Hello again, everybody, and welcome back to the second video of section 2.2 here in Precalculus. Once again, this is Mr. Gallagher. Hope everybody's doing well out there. And we are continuing in this video with the second half of section 2.2. And this is still polynomial functions. So really quick, just to do a very quick recap of what we've covered already. We talked about our odd and even degree functions. We talked about how we could use the leading term test to determine the end behavior of our polynomial functions. We also looked at the zeros and the turning points of our polynomial functions, and that's where we left off with the last video. So now I want to talk about something called the quadratic form of a polynomial function. So let's say you have a function like this example here, where I have h of x is equal to x to the fourth plus, minus 4x squared plus 3. And you want to look at the number of zeros and turning points. Well, we already know, because it's 4, based on the degree, we already know a couple of things about this graph. We already know that the number of zeros is going to be at most 4 zeros, and we know we're going to have at most 3 turns. But what are those zeros going to be? Well, those zeros are, we can determine what those zeros are by factoring, but this looks like a pretty hard problem to factor. X to the fourth minus 4x squared plus 3. In fact, if I set that equal to 0 in order to factor it, x squared, or x to the fourth minus 4x squared plus 3 is equal to 0. The problem is it doesn't look really easy to factor. There's nothing I can pull out. It's not a quadratic polynomial, so I can't unfoil it. But actually, that's what we're going to do. So what this concept up here is saying is that if I ever have a polynomial that is in this type of form, a u squared plus b plus c, meaning some sort of form that I can actually make it look like a quadratic, I can factor it. So what I'm going to do is I'm going to say, what if I decided this variable u was going to be equal to x squared? And what that means is I'm going to now replace x squared in my equation with a u and then see if it's a little easier to factor. Now, before I do that, let's take this x to the fourth. Can I change that and make that x squared squared minus 4x squared plus 3, right? Because x squared squared, that's the same as x to the fourth, right? Well, now I'm going to take this, and everywhere I see a x squared, I'm going to replace that with a u. So wouldn't that be u squared minus 4u plus 3 is equal to 0? Why would I do that? Well, now, isn't that easier to factor? U squared minus 4u plus 3. That's easy to factor, right? I'm going to go ahead and make that u, what is that? U minus 3 times u minus 1 equal to 0. And because I was able to factor it, because it was in a quadratic form, I made the problem easier. Now what I can do to actually solve for x is let's go ahead and replace that u back with x squared. So now I'm going to say x squared minus 3 times x squared minus 1 equals 0. And now I can solve it, because now that those are my factors, right? Don't I just set each factor equal to 0 and then solve for x, right? So that's what I'll do. I'll say, well, if x squared minus 3 is equal to 0, that must mean x squared has to equal 3, which means x has to equal, careful, I'll take the square root, that's going to be plus or minus square root of 3. That's going to be the positives, so x could be the positive square root of 3 or the negative square root of 3. But likewise, with the other factor, x squared minus 1 is equal to 0. Won't that be x squared equals 1, which means x could equal the plus or minus square root of 1, which is what? Positive 1 and negative 1. So those actually are my 4 zeros. Radical 3, negative radical 3, 1, and negative 1. And you could verify this. If you plug this into a graphing calculator, you're going to get a graph looking like this. And if you look at where does it cross the x-axis, at almost 2, which is the square root of 3, negative 1, positive 1, and then almost 2, which is the positive square root of 3. So those are my 4 zeros, and I verified that using graphing. So let's let you take a shot at this here. So your turn. So I want you to look at what are the possible number of real zeros, right? At most, how many zeros, and at most, how many turns is this going to have? And then I want you to factor this. Here's a hint. Can you pull something out first, and then can you use that U replacement technique that we just did? And then once you do that, I also want you to tell me about the end behavior. What's the end behavior here? What is the limit as x approaches negative or positive infinity? Go ahead and hit pause, and we'll reveal the answer in just a moment. Go ahead and hit pause now and work this out. Did you hit pause? Are you finished? If you're finished, you can hit play. If you're hearing me talk, then I'm assuming it's currently playing. So let's go ahead and reveal the answer here. What's my answer going to be? So the answer is going to be that it has at most 5 zeros and at most 4 turns, right? Because my degree is 5. So I'm going to have at most 5 zeros and at most 4 turns. Let's go ahead and factor it and see what those zeros actually are. So if you'll notice here, I set it equal to 0. I factored out an x to begin. And then I did my substitution of u is equal to x squared. And when I did that, I now replace this with u squared and 5u, right? Because that x to the 4th was really x squared squared. I factored it, and then I could plug the x squared back in, which is what I did down here on this last step. So now that I have this, can I set each one of those factors equal to 0? Sure. So I do that, and I get x equals 0. That's the first factor. X squared minus 6 equals 0. That means x equals plus or minus square root of 6. That's fine. But what about that x squared plus 1 equals 0? Well, that means x squared equals negative 1. X squared can never equal negative 1. So this solution does not work. So there are no solutions for that particular x squared or for that particular factor. So my only zeros are going to be what I have here. X equals 0, x equals radical 6, and x equals negative radical 6. Remember, we said there could be at most 5 zeros. We found 3 real zeros. Also looks like there's going to be 2 imaginary zeros with that x squared equals negative 1, but we're not going to count that. Likewise, let's talk about the end behavior. Because this is a positive leading coefficient, it's positive 1, and the degree is odd, we know that the limit of f of x of g of x, the limit of g of x as x approaches negative infinity, that limit is going to be negative infinity. And the limit of g of x as x approaches infinity, that limit's going to be infinity. And that's based on the end behaviors that we talked about in the last video. Sound good? Great. Let's continue on then. So we've talked about the number of zeros, the turns, and everything else. One other attribute that could happen sometimes with functions is sometimes we get repeated zeros. Let's go ahead and look at this function right here. I've got this h of x. The h should actually be down here. It looks like it got cut off on the top of the previous line. H of x equals x to the 4th plus 5x cubed plus 6x squared. Let's factor that. So what do I have? I'm going to have x to the 4th, x to the 4th plus 5x third plus 6x squared. I'm going to say equals 0. So I factor that. Well, the first thing I could do is I could pull out an x squared, right? So x squared times x squared plus 5x plus 6 is equal to 0, right? And then so factoring now, well, x squared becomes x times x, and this becomes x plus 3 and x plus 2, right? Equals 0. What are my zeros going to be? Well, my zero is going to be x could equal 0. That's 1. The second one, x could be 0 again. The third one, x could be negative 3. And the last one, x could be negative 2, right? So those are my 4 zeros. One of them is repeated, though. The 0 is repeated. So what we're going to say is we're going to say that 0 has a multiplicity of 2, meaning that a 0 occurs more than once. Well, the number 0 occurs as a 0 more than once, multiplicity of 2. What does that mean for our graph? Well, if you were to plug this into the graphing calculator, you'll notice something a little bit different about this graph. You'll notice that here are my graphs. I still have my a point at negative 2 and a point at negative 3. But then what's happening at 0? It doesn't actually cross the x-axis. It just kind of touches the x-axis and come back up. So when a graph or when a function has a multiplicity that's not just 1, that could change the type of zeros that it has, or what happens to the graph when it encounters that 0. And that's what we're going to talk about next. We're going to be talking about the repeated zeros of a polynomial function. Here's the rule. It says that whenever you have repeated zeros, and if it has a multiplicity that is odd, then what happens when the multiplicity is odd, well, then it's going to cross the x-axis at that particular point. But if it has an even multiplicity, like we just saw in that last example, it had a multiplicity of 2, well, then we're going to say it's tangent to the x-axis, meaning it just touches that axis and comes right back up. And that's going to happen when we have a zero that has an even multiplicity, 2, 4, 6, one of those values as well. So we can wrap everything up together that we've learned so far in this last example. So I want to go ahead and find the end behavior and the zeros and the multiplicity and the turning points, and then I want to go ahead and try to graph this particular function. So let's put it all together here. F of x is equal to x times 3x plus 1 times x minus 2 squared. Well, what's nice is this looks like it's already factored for us. In fact, I'm going to go ahead and let's write out the factors individually. This is really x times 3x plus 1 times x minus 2 times x minus 2, right? Because those factors there. So you can kind of already see we're going to get a multiplicity here in this one that's not 1. Let's talk about part A. Part A says, let's apply the leading term test, and let's talk about our end behavior. So what is my leading term going to be? If I were to multiply all this out, what would be the first term? Well, it would be this x times the 3x times the x that happens to be squared, right? So that means I'm actually going to get a 3x to the fourth. My leading term is going to be 3x to the fourth. Again, that is the x times the 3x times the x times the x. That's going to give me 3x to the fourth. What do we know about it? Well, it's an even degree and it's a positive leading coefficient. So that means what for our end behavior? The limit as x approaches negative infinity, meaning what's the left-hand side of the graph going to do? It's going to go up towards infinity. And then the limit as x approaches infinity, the right-hand side of my graph, what's it going to do? Well, it's also going to go up towards infinity. Because the positive leading coefficient with an even exponent or an even degree, it's going to go up on the left and the right-hand side. So there's our end behaviors. Next, let's talk about the zeros and the multiplicity. So, well, can I factor that? Well, it's already factored, right? We did that up there. So 3x plus 1. And then we have x minus 2 and x minus 2. So what are my zeros going to be? X could be equal to 0. X could be equal to, that's a negative 1/3, right? And then x could be equal to 2. Or x could also be equal to 2 again. So the one that has a multiplicity that's repeated, 2. 2 has a multiplicity of 2. Because 2 is repeated. Great. So I've got my zeros, I've got my end behavior, I've got the zeros and everything. So now I got to graph it. So what can I do? Well, here's an easy way to graph it. Take these zeros and can we look at all of the intervals around the zeros? So if I put these in order here, right? If I put my zeros, if I listed them as negative 1/3, negative 1/3, and 0 and 2, right? Those are my zeros. And if I look at numbers on all around those to see where some points on the graph might be, this would actually help me graph the function. So I need a point in this first interval from negative infinity all the way up to negative 1/3. What would be a good value to use? Well, negative 1's a good value to use here. So let's go ahead and use negative 1. If I plug in negative 1 to my function, what is f of negative 1? I'm going to get 18. So there's one of my points, negative 1, 18. And if I plug in, what's the number between negative 1/3 and 0? Let's try negative 0.1. I plug that into my calculator. I'm going to get negative 0.3. And then if I plug in, what's a good number between 0 and 2? Let's try 1. And if I plug in 1, I get 4. So 1, 4 is a point. So now I've got these 3 points. I marked them with red dots over on the side there. And can I graph those points and then also graph my zeros? And if you do that, you should get a graph that looks like this. So with the red dots, I went ahead and plugged in all of those. I plugged in the 3 points I have here. So I got negative 118, which is way up here. In fact, that dot's probably too low, but it's way, way up there, negative 118. Negative 0.1, negative 0.3, that's this red dot right here. And then also 1, 4. Well, 1, 4 is going to be that dot right there. And then what do I know about my zeros? Well, I know I have my zeros at negative 1/3, 0, and 2. So if you look in this graph here, negative 1/3 is going to be this dot right here. 0 is this dot right here. And then 2 is this dot right here. But remember, 2 had a multiplicity of 2, so it didn't actually cross the x-axis. It just touched it because it was tangent, because as we saw, 2 has a multiplicity of 2. So here was my graph going through the zeros, going through the points I graphed, and my end behavior, right? My limit as x approached infinity of f of x was infinity, and my limit as x approached negative infinity of f of x, that also equaled infinity. And that's it. So here's what we'd like you to try. We have an assignment out of the book, and it is not this whole assignment. In fact, this is not the right assignment. I'm going to go ahead and give you the right assignment here. So first of all, you can ignore this at the bottom, and you can ignore these even problems. We're going to change this to 13 to 21 odd. And that's an update that I did not make on my notes here. So we're going to do 13 to 21 odd and 23 to 31 odd. This is on page 104 and 105. So check these out in your textbook. And if you have any questions, you can email your teacher, myself, or Ms. Wybrick or Ms. Schmidt, and you can also post to the discussion tab in eCampus as well, and we're going to answer some questions there. And that'll be the assignment for this week. So each week we're going to, as we've mentioned, we're going to do a different section in here, and this is the assignment for this week. So I want you to go ahead and get these assignments done, and more details will follow about how to turn this assignment in. And that's it. So I hope this went well. Again, feel free to play this video again if there's something that you missed, and we will talk to you soon.